Hi, I'm Gary. Welcome back to my channel, Gary Does Solar. In my last video, we looked at the difference between kilowatts and kilowatt hours. A 101 guide, if you like, to power and energy. In this video, we're going to be covering AC and DC, alternating current and direct current, both fundamental concepts to any solar and battery installation. It won't take long, and a good knowledge of these will help you make better decisions about how you build your own solar and battery setup. Okay, let's get into it. AC and DC then, what is the difference between these two? AC stands for alternating current and DC stands for direct current. Let's look at DC first, as this is the easiest to understand. It's also what solar panels convert sunlight into before it's later converted into AC for use in the home. If you've watched my other videos, you'll recognize diagrams like this, where I talk about voltage across and current flowing through solar panels. On this particular panel, the voltage across the panel is 30 volts and the current flowing through it is 10 amps. But what do we actually mean when we talk about voltage and current, and how do they relate to each other? To find out, let's take a trip down memory lane to when we were at school making electric circuits like this. Here we have a battery and a bulb connected in a simple circuit. We refer to the battery as a source, meaning something that can generate power, and the bulb as a load, meaning something that consumes power. At the moment, the circuit is referred to as open because the switch at the top is open. Let's close that switch then to complete the circuit and see what happens. As you might have expected, the bulb lights up. But why is that? Well, we need to look at three different factors: voltage, current, and resistance. Let's start with voltage. Voltage is essentially the driving force of a circuit. It's what pushes electrical charge around the circuit, and it's measured in volts. The higher the voltage, the greater that driving force. In our example circuit here, this battery has a voltage of 1.5 volts as measured by a voltmeter. Voltage is always measured across 2 points in a circuit and is considered as a potential difference between those 2 points. Even if the switch in the circuit was open, the battery still has the potential to drive the circuit, and so the voltmeter would still measure 1.5 volts. Next is current. Current is a measurement of electrical charge passing through a given point in the circuit. Electrical charge is carried by electrons moving from the negative terminal of the battery around the circuit and into the positive terminal of the battery. And actually, this is one of the features of direct current. The current always flows in the same direction. Current is measured in amps, and we can measure the current in this example circuit by placing an ammeter into the circuit like so. The current is measured as 0.3 amps. If we were to place another ammeter into a different part of the circuit, say at the top, you can still see that the current still reads 0.3 amps. As an analogy, you can imagine the current as being like water flowing through a pipe, and the voltage is the pressure of that water in the pipe. To see this better, I've recreated our little circuit using water here. The battery might be a turbine creating the pressure, akin to voltage, which causes the water to flow at a particular rate, akin to current. And instead of the bulb, another turbine is used that can translate the power of the flowing water into something useful. Okay, back to our electrical circuit then. We can now look at the resistance, which is the difficulty the current has passing through an element in the circuit, for example the bulb. Resistance is measured in ohms, and we can measure the resistance of the bulb using an ohmmeter. It happens to be 5 ohms. We'll ignore the fact that the bulb's resistance might change as it heats up. Now voltage, current and resistance are related. Voltage is equal to the current multiplied by the resistance. V equals IR. And we can see here in our circuit, if we multiply the current 0.3 amps by the resistance 5 ohms, we get 1.5, which matches the voltage we're reading. We can also work out the power of the bulb, knowing the voltage and the current. Power is voltage multiplied by current. In our case, 1.5 volts times 0.3 amps gives us 0.45 watts. If we rearrange the top formula, we can calculate the current if we know the voltage and the resistance of the bulb. This will be useful for us as we reconfigure the circuit. Okay, let's switch it off and add another battery in series with the circuit. As we know, the voltage across each battery is 1.5 volts, and when we add batteries in series, the voltage simply adds up. We're now measuring 3 volts across both batteries. With the switch open, we're of course measuring 0 amps, and as we know the resistance of the bulb, 5 ohms, we should be able to work out the expected current. 3 volts divided by 5 ohms equals 0.6 amps. Okay, let's throw the switch and see what happens. Wow, that's bright. We are indeed getting 0.6 amps. Great. What about the power? Well, we can easily work that out using the formula we used before. 3 volts times 0.6 amps is 1.8 watts. What's interesting is that you might think by doubling the voltage you would double the power, but in actual fact the power is now 4 times as much as before. Who'd have thought? Okay, that bulb's pretty bright. Let's switch off the circuit so we don't burn it out. And let's add another bulb in series. We still have 3 volts across the batteries. What will happen now if we switch the circuit on? Well, we can see the current is 0.3 amps, the same value as when we had 1 battery and 1 bulb. And this makes sense if we use our rearranged formula from earlier to calculate what the current should be. The resistance across both bulbs is simply the resistances of each bulb added together as they're in series. So the current is 3 volts divided by 10 ohms, and this gives us 0.3 amps. What does that mean for the power of each bulb then? Well, let's measure the voltage across each bulb. You can see that the 3 volts from the battery splits equally across the bulbs, 1.5 volts each. As we know, both bulbs have a resistance of 5 ohms, so we can work out the power of each bulb. 1.5 volts times 0.3 amps gives us 0.45 watts, the same power we had when we had 1 battery and 1 bulb. Okay, let's switch off the circuit again and remove one of the batteries. What do we think the current will be when we switch the circuit back on? As it happens, the current looks to be half what it was before. Let's calculate that using our handy formula once more. We have a voltage of 1.5 volts and a total resistance of 10 ohms. This gives us a current of 1.5 divided by 10, which is 0.15 amps. Okay, how about the power of each bulb then? Well, the 1.5 volts splits evenly across the bulbs as before, so that's 0.75 volts across each bulb. The power is then 0.75 volts times the current, 0.15 amps, and this works out to 0.11 watts. You might have thought that the battery with 2 bulbs would be half as bright as the single bulb, but actually the bulbs are 4 times dimmer. Okay, let's switch off the circuit and try something a bit different this time. We're going to add a second bulb in parallel to the first. We'll add in a few ammeters first to see what's happening with the current, especially now that there is more than one route it could travel. Then switch it on. We can see there is now twice as much current flowing from the battery as before, and that 0.6 amps splits into 2, with 0.3 amps going to each bulb. The brightness of each bulb is the same as the brightness of the single bulb with the single battery. Why is that, given the brightness was so low with 2 bulbs in series? Well, let's check the voltages to find out. We know that the battery voltage is 1.5 volts, but we can see that the voltage across each bulb is also 1.5 volts. We know the resistance of the bulb is 5 ohms, so we can confirm that the current into each bulb would be 1.5 volts divided by 5 ohms, which is 0.3 amps. So for parallel circuits, we can see that the voltage remains the same, but the current splits. Finally, we can work out the power of each bulb. That's 1.5 volts multiplied by 0.3 amps is 0.45 watts. Just to complete the picture then, let's add another battery in parallel. And we'll also add another ammeter so we can see what's going on with the current now. There's no change to the brightness of the bulbs, but now each battery is only supplying 0.3 amps. That means that 2 batteries will last twice as long as 1 battery, and that makes sense. Hopefully that's given you a good understanding of how DC works, and how you can perform simple calculations with voltage, current, resistance and power. Let's relate this back to your own solar installation then, particularly the solar panels. A typical full cell solar panel for domestic use contains 60 cells. Each cell, when exposed to sunlight, starts generating current, just like a small battery. You can consider this solar panel then as a collection of 60 small batteries all wired in series. Each battery has a voltage of 0.5 volts, so that's 30 volts in total for the panel, remembering that voltages in series add up. Collectively, these batteries, solar cells, generate a current of 10 amps, and from our power equation we can calculate the total power output of the panel as 300 watts. Let's compare this panel with a half-cut cell panel. In such a panel, each half cell has a voltage of 0.25 volts. There are 120 half cells making a total voltage of 30 volts, just like for the full cell panel. But there's a difference in the way the half cell panel is wired. You can see that current coming into the panel splits upwards and downwards 3 times before leaving the panel. So that's 10 amps coming in, splitting evenly into 5 amps each way. The total output is the same as for the full cell panel, but the half cell provides better performance for certain kinds of shading. You can find out more about half cell panels in this video I made, the link to which is in the video description. Let's zoom out now and look at an array of panels on the roof of a property. Here we have an array of 12 of these particular half cell panels, all connected in series on a house here in the UK. Because this inverter, and indeed most inverters, can support 2 separate strings, we've split the panels evenly into 2 strings of 6 panels each. Adding up the voltages of the panels in the first string, we have 6 times 30 volts, which is equal to 240 volts. And because we already know the current at peak solar generation will be 10 amps, we can work out the maximum power output to be 240 volts times 10 amps, which equals 2.4 kilowatts peak. The same is true for the second string of panels, and that gives us a total maximum power output of 4.8 kilowatts peak. So everything we've talked about so far has been DC voltage and current. But as you can see, the string inverter converts the DC into AC so that it can be used to power all the AC appliances in the house. But here in the UK, the mains voltage is 240 volts. And if each string is already producing 240 volts, why do we need to convert it to AC? Can't we just feed that DC straight into the house? Do we even need AC? And what actually is it? To answer these questions, we need to turn back time by more than 140 years to get to 1882. This is Thomas Edison, the American inventor. You might know him as the inventor of the electric light bulb. He didn't actually invent the light bulb, but he was the first to come up with a bulb that was cheap, practical, and long-lasting. He also came up with a solution for supplying electricity to homes, offices, and factories to power his bulbs. His first electricity generating station was built in Manhattan, New York, and comprised 6 of these coal-powered dynamo generators that produced DC electricity at 110 volts. That electricity was then delivered to customers via underground cables. And here was the problem with DC. The power losses due to resistance in the wires meant that this power station could only supply properties within a 1 square mile radius. To cover all of Manhattan then would have taken quite a large number of these generating stations, and it would have been impossible to supply electricity to properties outside the cities because of the distances involved. The power losses would have been too high. Those power losses could be reduced if the voltage was far higher. Remembering our formula, power equals voltage times current, and for the same power, the higher the voltage, the lower the current required, and therefore the lower the resistance losses in the wire. But at the time it was complicated and expensive to change from one DC voltage to another. And whilst it might be cost feasible to step up the DC voltage at the generating station, it was cost prohibitive to step down the voltage again at the other end in order for the transmitted power to be safely consumed. Additionally, the DC motors that were available at the time used to power factory machinery were complex, unreliable, and had low power outputs. And so for electricity to be generated and usefully consumed in factories and homes across the whole country, another solution had to be found. By the way, don't forget to hit like on this video if you're getting a lot from it. And please also subscribe to see my future videos. The next one will be all about microinverters and why I think they might actually be the future of domestic solar. Okay, enter this man into the frame, Nikola Tesla. He was a genius, and one of his many inventions was the induction motor. What was special about this kind of motor was that it was powered by a new type of electricity, AC, or alternating current. The design of this motor was revolutionary, simple, inexpensive, powerful, and reliable. Not only that, but this motor could generate AC as well. With Thomas Edison standing firm with his DC solution, and now Nikola Tesla coming up with his alternative AC solution, it wasn't long before the war of the current started. And what a war it was! There are plenty of YouTube videos available that cover this topic, and I'd also like to recommend this Hollywood movie that was made a few years ago called The Current War and starring Benedict Cumberbatch. Okay, before we look at the benefits of AC over DC, let's first understand what AC is. In a DC circuit, current always travels from the negative terminal of the power source through the load and back to the positive terminal. If we swap the DC power source for an AC one, it behaves very differently. At first, the current travels from the negative terminal through the load to the positive terminal, but after a short time it reverses direction and flows the opposite way. And a short time later it reverses direction again and flows from the negative to the positive terminal again. This cycle repeats a number of times a second. In the UK and Europe, this frequency of change is 50 times a second, or 50 Hertz, and in the US and some other countries it's 60 Hertz. It's easier to understand the difference between DC and AC current flow if we plot them on a graph. DC is straightforward. The current flows in one direction only at a constant voltage. AC is a little more complicated. The current flows in one direction to begin with the voltage growing from 0 to a maximum level before declining back to 0 again. Then the current starts to flow in the opposite direction, with the voltage going negative for a while, and the cycle repeats. But how can such a complex waveform be generated in the first place? Let's bring in Tesla's induction motor, which is essentially a rotating magnet with a north and south pole mounted inside an assembly with electromagnets on each side. Each electromagnet is essentially nothing more than copper wire wound several times around a ferrite core. When electricity is passed through the copper wire, the core acts like a magnet, either repelling or attracting the rotating magnet, making it spin. Here though, we're using the motor as a generator. We're going to burn coal and use the heat generated from that to spin a turbine which is attached to the generator. The moving magnets inside the generator will interact with each other and generate AC electricity, exactly like the AC waveform we saw. The speed at which the generator spins will determine the frequency of that wave, either 50 or 60 Hertz. Now, if we add a Tesla induction motor at the other end, we can use that waveform to spin that motor so it can be used to power factory machines, etc. Okay, so AC electricity allows for more powerful and efficient motors than DC could, but how does it solve the bigger problem of power loss when transmitting electricity over long distances? So here we have a generating station at the top left, and we want to get the electricity to the house on the bottom right without losing too much power on the way. Today's generating stations typically output AC at 22 kilovolts, which is already far higher than the voltage we use in our homes, but it's not high enough yet. We need to step up that voltage to anywhere between 150 and 750 kilovolts using a series of transformers. Like an induction motor, these transformers are incredibly simple in design. They're just two sets of copper wire wound around a ferrite core. There are no moving parts. What's key is that there are a differing number of windings on each side. When stepping up, the left-hand side with fewer windings induces a much higher voltage in the right-hand side. Now, the overall power doesn't change during this process, so if the voltage increases, the current must decrease, remembering that power equals voltage times current. And that decreased level of current is important, as we'll see in a moment. We can now send the AC over power lines across the country, and those power lines can run for hundreds of miles with only a small loss of power on the way. Why is that? It's because even though there is resistance in those power lines, an extremely low current means extremely low resistive losses. At the other end of the transmission line, the AC is then stepped down, again using a series of transformers. You can see that for domestic properties, the final voltage is a comparatively very low voltage of between 110 and 240 volts, depending on the country. Finally, this voltage is then fed into the house on the diagram. While we're here, it's worth taking a minute to look at what single-phase and three-phase AC is. The generator we used in the example earlier was a single-phase generator, meaning that it generated a single AC waveform. But there's space inside that generator for a few more electromagnets. So let's add some and see what happens. You can see now that we can generate 3 AC waveforms all at the same time, with each waveform being at a slightly different phase or angle to the others, hence the name 3-phase. You could add more phases inside the generator if you want by adding more electromagnets, but from a physics and also a practical point of view, 3 phases provide the optimum efficiency, not only for generation but also for transmission and distribution. For a single phase you need 2 wires on the pylons, but for 3 phases you only need to add 1 extra wire. Here's how it works in reality. The generating station generates 3-phase AC and distributes that to factories and houses across the country. Factories, because they operate heavy machinery, will usually take all 3 phases, so all 3 wires will be used. but domestic properties will typically only require a single phase. So what usually happens within a street is that each property will use only 2 of the 3 wires, but a different combination of those 2 wires each time. In our example here, the last house elected to have all 3 phases, perhaps because they wanted to make use of a 3-phase EV charger. Once the AC power arrives at the house, we can now look at how it's consumed by the various appliances in the house. And just like we saw with DC, everything is connected in parallel to the incoming supply, meaning that all the appliances operate at the same voltage, consuming the current they need. It feels like there's no limit to the number of appliances that can be connected, as the incoming supply seems to have a limitless current, but there is a limit, which is determined by the size of the fuse connected to the meter of the house. In the UK, for most modern homes, this fuse is 100 amps. There will also be other fuses or breakers inside the consumer unit of the house, and depending on the country, the plugs of your appliances may also have a fuse in them. Coming back to your solar installation then, given that AC was the winner of the current war, you can now see why we have to convert the DC power coming in from your panels into AC. But things that were not possible with DC 140 years ago have since become possible. Most recently, in the last couple of decades, transmission of DC power over vast distances, thousands of miles, with even less power loss than AC. The technology is called HVDC, or High Voltage Direct Current, and it's too much to cover in this video, but the benefits of it are amazing, so I'll put a link or two about it in the video description. I hope that through watching this video you've now got a good grasp of AC, DC, voltage and current, and how these all relate to your solar setup. If you'd like to support my channel, here is my referral code for Octopus Energy, and if you sign up using this code, you'll get a £50 credit onto your account, and so will I. Thanks for all your support, and see you soon in the next video.